All right, you guys ready for a busy lecture? Are the lights okay there? Can you still see okay? Yeah, it doesn't seem to be pointed right at the screen, which is kind of cool for a change. Makes me look a little dark on the video, but that's okay too. It doesn't show up on the recording. Okay, they've changed the way they do video encoding on WebEx. While we were all on spring break, they apparently were busy coding. So it froze my video yesterday in one of the lectures. If you just happen to see me like freeze, please let me know, because although I don't really care about the video being frozen, it makes me nervous that the rest of it's being frozen as well. And respect to the movie, but I don't like Frozen. Okay, we had gotten up to, I want to say, past this actually. I think we were well into this. Let me just take one quick peek. I know exactly where I was yesterday, but I want to make double sure. I can't figure out why, but I seem to be missing some lectures as well, which drove me crazy. Okay, I think this is what I want right in here. Yeah, but I don't know if we got past that, or yeah, we did, kind of. Okay. 244. So we were kind of up near the top. All right. We had sort of ended up in this arena last time, but this slide is basically trying to show us is that once we pick a maximum window size, we are going to alternate as we go throughout the day between reaching that number and then experiencing a collision, because we always are pushing the limit and we're always trying to send as much as we can. So once we get close to the window size, it by definition should be close to the maximum amount of bandwidth we can get out of the network as our fair share. So we'll have a loss, and when we have a loss, it's not because the network went down, it's just because we pushed it a little bit. And so the evidence that we'll receive that there's a loss is different than the evidence when the network goes down hard. And so we'll talk about both of those things. And we talked about them before, but I'll recap those. But in that situation where the network is still functioning pretty well, and we think one packet's missing, but maybe the ones after it still look like they're getting there, then instead of overreacting and backing all the way off and stopping what we're doing, we'll instead just cut our bandwidth in half. We'll stop sending packets at the size we were, and we will reduce our window size by 50%, so that the next round, when it's time for us to send packets again, we'll only send half as many. Now, when I say we're going to slow down, it doesn't mean the bandwidth reduces. It's still going to ingest the same number of bits per second. For the number of packets that we send, we're still going to send those as fast as we can onto the network, but we're just going to stop after sending half the number of packets as before. So that's shown by the bottom part on this graph, and we will inch our way back up, and if things work out great, then we'll reach our maximum window size again and cut it back down again. So our window size is actually defined as exactly how many packets we sent that round. So what we're really doing is changing the window size as we go up. But if you just let me define this other variable for a moment and pretend that W is kind of the goal, then we will spend our day oscillating back and forth between these two. We'll get up to this point, we'll experience a loss, we'll cut it in half. We'll inch our way back up again. So at this round, we're sending however many packets this is. So if this is the number 10, for example, then W over 2 would be 5. And let me copy this over so I can draw on it a little bit and show you maybe by sketching it. Sorry for the completely crazy drawing, but we're going to build one just as crazy ourselves today. So I'm not going to apologize too much. I would be lying. Okay, so what's going on basically here is, as you go across the x-axis, you are sending round after round of packets. So each one of these is a different TCP round. Well, what does that mean, a round? Do you remember when we looked at the way TCP behaved? It tends to be that we send an entire window's worth all at once as quickly and close together as possible, and then we wait around for it to arrive at the other end, and we get all the acknowledgments back in a big batch as well. We saw that with the simulators. I'd go click, 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 and the packets would start working their way across the network, and they get to the bottom, and the acknowledgments would start climbing their way back up again. So that's a round. We might as well call this time, since there's a period of activity and then some waiting and then responses, we'll call that a transmission round. So that's the way TCP works. If you watch TCP on a network, you'll send a batch, wait a little bit, get responses. Send another batch, wait a little bit, get responses. Send another batch, wait a little bit, get responses. So each one of these vertical lines I've drawn in this graph up here are basically pointing to those rounds. And so my window size is growing round by round, linearly, one by one by one, until I get up to this point here. And in this round, I experienced a packet loss that caused me to cut my window size back in half again. So if I want to look at the variable name that's really being used here, it's congestion window size. So here, if this was a 10 and this was a 5, then my congestion window size is 5, 6, 7, 8, 9, 10, 5, again, 6, 7, 8, 9, 10, 5, 6, 7, 8, 9, 10, and so forth. In reality, it's never going to be quite this smooth. It's going to, if all you experience are these types of losses, it's still not going to happen at the same time every time. It'll look more like this, but you know, it's still got the same shape. It's a sawtooth type of design. So that's the goal. And when TCP is working perfectly, it looks like this. We're always getting our fair share of the bandwidth. We're always trying to see if we can get a little more with every round by sending one more packet in a window than we did the time before. And once in a while, we'll have to back off by half. And the reason we back off by half instead of just backing off by one is congestion is very dangerous. And if you begin to cause congestion in a router, you can quickly overwhelm it and it will drop everything. And every packet it drops has to be retransmitted. So if you start dropping packets, you're going to save yourself no bandwidth at all if everything has to get retransmitted. So what you want people to do when there's congestion is to just back way off for a moment and give the router a chance to catch up. Backing off just one isn't going to give the router a chance to back up, to catch back up again. So there's even more dramatic reaction to losses that we'll see today as well, and that's what happens when you feel like the network's gone down. And you'll evidence that by a timer going off. When that happens, as you'll see, we'll go all the way back down to 1. So we'll drop all the way down to here, and we'll start climbing our way back up and then going back up. So this is exponential growth, and this is linear growth. So I'm going to come at this 20 different ways today to try and give you different angles to look at this, and hopefully by the end of the lecture, you'll have your head wrapped around it. All right. So as you can see, if TCP is working well and you do this during the day, then on average, your average amount of throughput is like in between W/2 and W. In other words, it's 3/4 your window size. So it's a weird number, but that's what you should expect to get. Not half, not full, 3/4. Okay, and you'll see that graph again in a little bit. So TCP is not originally designed to work on as many different types of networks as we've made it work. There's a really, really good interview made by, I can't remember who did the interview. It may have been the communications of the ACM, but it was with a professor in California who started off at MIT, sort of heard one of the very, very early talks on packet switch networks, and decided when she was looking around for a PhD topic, like this is it. This is what I want. And she's gone on to have this crazy successful career and proposed some things that were adopted as part of TCP and has a whole team of PhD students at any given time. I should be so lucky as to work with somebody like that. But she made it onto a list first couple of years ago called, I want to say it's like the H factor. Let me see if I can find it. I can never quite remember the name of this. I can never quite remember the name of this freaking list. I remember the first letter is H. Here it is, H index. Okay. Here it is. All right. And it's a list of the people who are the most cited authors in computer science. And there have been lots of studies to try and figure out, well, are all citations equal? I mean, if you get cited in the communication for something you wrote in the communications of the ACM, isn't that more valuable than if you got cited for writing in Bob's Houston PC Users Group magazine? I mean, so there are people who've like come up with weighting and things. But basically, what this is showing is the top most referenced authors in computer science. And this includes Nobel laureates and lots of IEEE fellows and ACM people and things like that. But this lady that I mentioned in here, let me see if I can find her, because I spent part of the weekend, here she is, by kind of going through this stuff. Here she talks about, and she started kind of the same time I did, which was sort of cool. And she gave this really, really good article and talks about, this isn't the article, this is just her bio. I'll find it and drop it out there for you guys, and I may pop it in an email. She describes kind of why TCP is still valuable, why it's able to survive and still work after all these years. And one of the things that she points to is its unbelievable flexibility, that it had lots of flexibility built into it, and as a result, it's proven to be malleable and can be fitted to lots of different kinds of networking problems, including data centers and long fat pipes. So long fat pipes are ones where the round trip delay is quite significant, and the bandwidth of the network is enormous, way in excess of anything that we experienced maybe early on. We had long transmission lines from Boston to Los Angeles that took 30 milliseconds to get a packet from one end to the other. So that's not something that got invented, recently. But combining that with very high bandwidth is something that's unusual. So TCP's got to adjust to kind of make sure it works well. And here's why. There's a flaw if you just use TCP out of the box the way it is. And the problem is this. Suppose that W, the window size where you have reached the capacity of the network, is, I don't know, more or less 100,000 packets. And so half of that is 50,000 packets. And the way TCP works is you grow exponentially until you get to this point, because this is the threshold where you end running in this algorithm slow start, where you grow exponentially, and you switch to congestion avoidance, where you grow linearly. So the goal is to get as fast as you can to this SS threshold value, and then just grow linearly from there, because now you're in kind of the danger zone where you're going to drop something. Well, if I'm growing from 1 MSS up to 4 or 8 or 16, that doesn't take very long. But if I'm growing up to 50,000, it takes a while. And I know perfectly well this network, I'm not sharing this with a million other people, it's my router on the end of this thing. I'm a carrier, that's the only person that's going to have a network this big. And so the carrier has total control over what's happening on this network. They will never introduce more packets onto this wire than it can handle. They can't. So they'll do lots of traffic shaping at ingress to prevent overloading and things like that. So why not just start off right here with that sawtooth that we saw and get on with it? In fact, they may not even like this. They may say, just run it like an inch below this black line. I'm trying to draw right underneath it. Why not just do that? There's no doubt here on what's going on, but what we do with regular TCP is we take log base 2 of 50,000 number of transmission rounds to get up to even the base. Too long. Takes too long. All this time is wasted bandwidth. So if I drew this out as a graph, what we're trying to achieve here is, let's say this is 100 milliseconds round trip time, and this packet is 1,500 bytes, and my bandwidth on this network is 10 gigabits per second or higher. What I want to get out of it is actually 10 gigabits per second throughput, so probably higher than that. So if I start off with a window size of 1, what it means is I send one packet, and I wait 100 milliseconds, and I will get an acknowledgement back. During that 100 milliseconds, I actually started transmitting a little bit before that, and the first bit took 100 milliseconds to get back, but the last bit didn't arrive at the same time as the first bit. The last bit arrived a little bit after, and just up here at the top, I also sent the last bit a little bit after the first. I mean, it does take some amount of time to transmit 1,500 bytes, to transmit 12,000 bits. So we should count this as 100 milliseconds from the time I start sending the first bit to the time I get the acknowledgement back to the first bit, assuming this guy is like super fast to respond over here, plus a little bit extra to wait for the rest of the acknowledgement to arrive. All right, so that's 100 milliseconds plus a tiny bit more. So what's the utilization of this? It's like a microsecond over 100 milliseconds, something tiny, tiny utilization. So what we know we want to do is actually use more of this time to send more things and then continue to get acknowledgments back in a big stack as well. Now, a much greater percentage of this time is spent actually using the network, actually transmitting new bits onto the network. So if you can get this up to the point where you're sending 10 billion bits per second on this network, you will have reached 10 gigabits per second throughput. So how many packets is that going to take? Well, that's where we got this 83,333. That's an enormous window size. And we're going to start at 1 and grow, then to 2, then 4, then 8, then 16. Yeah, exponential is fast, but it's still lots of transmission realms. So what this basically means is you are going to wait for 1, and then you're going to send 2, and then you're going to send 3. And in every one of those, you could have been sending 83,000 instead of 1, 83,000 instead of 2, 83,000 instead of 4. So you're wasting tons of time, and your users are like, what's up with the network? I thought you had a fast 10 gig network. Why are the packets still sitting in the queue after so long? So that's a problem, and it's similar to ones that we have in data centers as well. TCP throughput, basically, in this slide is trying to measure, so if you did that and you didn't want any retransmissions, I mean, if you just wanted to send 83,333 and you wanted them to all get there, you don't want to pad this number at all to like maybe 84,000, just in case you have to retransmit a few hundred of them. If you just want to make it perfect like that, then the loss error rate is going to have to be 2 times 10 to the minus 10th. In other words, forget it. Doesn't exist. Not going to happen. You can't build one network. There's no communication technology that has that error rate. However, you can build constellations of networks that do. You can build a network that's got 3 fiber rings that leave your building in 3 different places and go 3 different routes and arrive at the destination 3 different sides of the building. We used to design those all the time for people. We usually use 2, not 3. But if you want to be super sure that you never lose anything, maybe 3 is better for you. And you just send a copy of the same data on each one. So you double or triple the amount of bandwidth, and if one of them has an error, then you still have the other one. So we used to screw this up all the time in the phone company. We used to do things because the guys that are installing the fibers are construction workers. Now, they work for the phone company. They're highly skilled in doing telecommunications stuff, and they know all the laws for rights of way, and they're really good at repairing damage they do to roads. And we used to always feel like we were the best at doing that, so let us run your stuff. But they would basically start at the start point, and we would say, look, we need 4 fibers to this cabinet at, I don't know, Lyondell Petrochem. This is one of the people we did this to. And we need them to run from this Lyondell Petrochem site to this one over here on the other side of town. It needs to be redundant. And they go, okay, you need 4 fibers. So they'd run 2 fibers this way. They'd run a pair of fibers. Great. And they'd run a pair of fibers this way. And then they send the guy in to finish the installation inside the building. And what he would do is he would take this fiber and plug it in. Let me switch colors. He would take this fiber, plug it in, and he would make it the input signal, because fiber is only one direction, so it's either coming or going. Input for the left side, and what you want is for this to be the output for the left side. And then this side over here would be the input for the right side and the output for the right side. So what we ended up doing was that we took this fiber and made it the output, and we took this fiber and made it the input, and this fiber made it the output. Does anybody see why that's a problem? You still have all 4 fibers. Each one is connected to one signal. They're going to the other end. What is this intended to try and ensure against? Failure. What's failure? What's the worst failure you could have on a network? The worst failure you can have on a network is this guy, right? So these guys are always out everywhere, digging around, doing stuff, and they dig all your crap up. We had one guy, one crew in the medical center on Fannin at Holcomb. They were digging a sewer line for a new building going in. And sewer lines, you know, they're like this big around. And what you do is you run a little auger, little tiny thing, an iron rod that you can curve, and it goes under the street and stuff, and you get it over to the other side, and then you dig a hole down, and then you lower this big giant drill bit. And you pull the drill bit back with this steel rod. And the drill bit is spinning, and all it leaves is smoke and a hole, exactly the size of the sewer line you need. And then you can put the concrete big circular things that you see sitting on the side of the road. Sometimes you can put those in there. Well, when they did that, they just pulled all of our crap up, thousands and thousands of telecommunication lines for all the medical center institution. So you want fiber rings to avoid this kind of problem. Here's the deal. Let's say this guy cuts this one up. What have you lost? You've lost the input to the left side, so the left side ring is down. And because I didn't run these correctly, this guy over here, if you can see, goes over here. I've lost, I don't know, maybe the input or the output, but you've lost something from the right ring. You've taken them both down. What you want is input and output for the left ring on one side of the box and input-output for the right ring on the right side of the box. You do not want to cross one of the fibers on each side. It just doesn't help you at all. So we used to regularly do this, and you know, I would have to go out and like mea culpa, I'm so sorry, we're getting it up right now, and taking a look at the design. And then we get back to the office and like, do you guys not test this stuff? You know, what you're supposed to do is then go to this little patch panel at the side of the, you know, the side of the building and just try pulling one of the pairs out as it's going into the ground. Just yank it out. Oh, we don't want to do that. Well, why the hell not? Well, because we're afraid it'll go down. Yeah, let's do it down before we start billing the customer and figure out if it works instead of pulling it out and having it go down now when I have to write them a $20,000 check, you moron. So we would always have these back and forth. And so every once in a while, I would say most of that to myself. I'd close the door and we would all laugh about it. And we would like, please, could you please check the fiber for us? So they were really good at what they did. And out of 100,000 networks, they might get a few of these wrong like that. But God, it was painful when it happened. It was just awful. We had one crew. Oh, by the way, back to this crew in the medical center. What they did when they started pulling this up and they saw all these fibers and you're like, there's all this stuff that you pull out. They're like, oh. And so they push dirt back in the hole and run. They flee. They get back in their little, you know, car or whatever they came in, and they leave. And you know, these construction guys, they hire manual laborers to do this stuff. They don't know anything about telecommunications. So that's why we go out and we paint stripes on the ground, and they're supposed to like pay attention to it. So all that basically does when that happens is we take them to court and get $1 million out of them to pay for all the damages and all the contract violations we had. And they have to pay it because they violated the law by not following those paint stripes. So if you submit records to this company that goes out and paints this stuff and you do not mark where all of your stuff is, and therefore they do not paint where on the sidewalk it's on top of, and the people then therefore dig it up, it's your fault, not theirs. All they have to do is call in a locate, and somebody shows up within 24 or 48 hours, and they spray paint all of the utilities that are around that area. So that's what all that graffiti is that you guys see all the time. And I think you know that, right? We did that. All right, so you want this stuff to kind of be that kind of be redundant as well, but you'll never have a network otherwise that's ever going to get anywhere near this type of error rate. Another goal of TCP is to be fair. And one of the things that's most magical about TCP is TCP will only use its fair ratio of the bandwidth on the network. So like if it's a gig in bandwidth and there are 10 people sending TCP packets on it and they're all trying to go as fast as they can because they have a lot of, endless supply of packets to transmit, on average, none of them will get more than 1/10 of that network. If there's 10. If there's 5 of them, 1/5. If there's 100 of them, 1/100th. This is true despite the fact that nobody knows the amount of bandwidth, and nobody knows what their fair share is, and nobody knows how many other users are sharing the link with them at the time. Nonetheless, without knowing any of that, you still get your fair share of bandwidth on average, no more, no less. So it's kind of magical. And the way you do it is by paying very close attention to when you have losses, because that means it's full, and you back off, but not too much. And if you work out the algorithm correctly, and everybody's doing this, everybody kind of reaches a steady state of about 3/4 their window size. So this lady, Lixia Zhang, I don't know why I always call her Lydia, she helped with that work, along with a guy named Dan Jacobson and some others. But she's a rock star. And so she ended up on this list of the most cited computer scientists. And to be on that list, by the way, you were in the top 0.005% of computer scientists in the world. There's like, I don't know, 170, 200 of them out of 7 million, or however many of us there are at this point. So it's kind of interesting. So what this is basically showing is, with properly functioning TCP and with properly functioning buffers and routers, your bottleneck will be shared equally among all folks. That's our goal. Now I'm going to show you a graph that, to me, has never really made complete sense as the best way to show what they're trying to get across here, but we're going to go through it, and maybe it'll click for you guys. So what this graph is showing, and I will copy it over because I need to scribble on it, of course. I can't resist the urge. I mean, I just make these things a bloodbath. I don't just draw on them, I mutilate them. It's unbelievable. Okay. All right, so here's a graph, and I have 2 users. I have user 2 over here, user 1 down here, and this is the amount of bandwidth on both axes that they each get to use. So the size of my pipe is R. So if user 1 is using 100% of the pipe, then user 0 or user 2 has 0% of it. Well, that makes sense. And if user 2 is consuming 100% of the pipe, if you look here on this line, then user 1 intersects this point at 0 as well. So what you're hoping for is that on average, this guy's using about 50%, and this guy's using about 50%. And it's okay if they fluctuate, and they will fluctuate because the window sizes have that sawtooth pattern, but that's what you basically want to see. So you can draw that orange line as the graph. That is the log. That is the total amount of bandwidth. At any point along this graph, if you add x plus y, it will equal r. And you should convince yourself of that. Right? So the amount of bandwidth I'm using plus the amount of bandwidth I leave over for the other guy to use can't ever exceed the bandwidth of the network, the capacity of the network. Okay, well that makes a little more sense to say it a little bit that way. So what's gonna happen here? I might pick a point here, and what I'll actually do is start off using less bandwidth too much, and I will move my way up across this line and use too much. And let me draw this line a little bit. I'll use too much, and I will drop a packet, and I will pop off again. And what you'll see will happen over time is I will end up steady stating my way here. And the other guy is doing the same thing. So that's what the graph tries to show you. It's just never made tons and tons of sense to draw it this way. It's just never really totally clicked for me. But that's basically what they're trying to show you, is a way of sharing it. And you'll notice that these red lines, and hopefully mine too over here, the orange line intersects these things at about 3/4 of the window size. So if this is your window size here, and this is your window size over 2, then this is about 75% of that. So that's the other thing they're trying to show you in this. All right. So you've got 2 competing sessions, and this multiplicative decreases the throughput proportionally for the 2. So you end up hopefully with an equal bandwidth share. Okay. So fairness with UDP is a little different. UDP doesn't bother doing a handshake. UDP doesn't notice that a packet's been dropped. It doesn't try retransmitting a packet. Why would it? If you're doing an audio link, does it really do you any good to receive a missing 1/100th of a second audio clip 2 seconds after it was supposed to be there? It's not like you're listening along and go, I think I get it, and then this missing clip shows up from 2 seconds ago, like, ah, genius, I get it now. No, it's not. Your brain doesn't work that way. It's like watching a TV where there's static or listening to a radio program when there's a little static. None of that, as long as it's not too bad, and none of that prevents you from understanding things. And there's actual scientific measurements for voice, particularly, they basically a scoring mechanism, a mean optimized score or MOS standard. And there's some really good papers. I was very surprised and very impressed by a bunch of the papers that were published by Microsoft after they bought Skype. And they started publishing kind of the rigor that the Skype engineers had gone to try to write algorithms that monitored audio quality. And they did it in a way that was just as good as a Bell scientist I'd ever seen do it. And I was like super impressed. So my conclusion, of course, being arrogant, which is like everybody that's worked at the phone company long enough has what they call a bell-shaped head. And so here's a perfect example of that. When I saw that the work they did, I go, oh, they must have come from the phone company, because only people from the phone company could be that smart and do that. I mean, that's how arrogant. It's like complete, utter nonsense. I seriously doubt they were. But that was the first thought that crossed my mind. So I guess maybe pride is part of that too. Maybe it's not all bad. Anyway, it's with UDP, you don't bother retransmitting, you don't bother keeping track of stuff, and they don't want stuff throttled by congestion control. They just try to dump everything on it, and they push other people out of the way. That's their problem. So fortunately, the routers are usually agnostic, and they will throw away the same percentage of UDP's packets as they're throwing away everybody else's streams as well. So for this reason, some people block UDP traffic coming into their network. They just will not allow it in unless it's in response to a query made by a user inside their network. So if you open up a YouTube video, then yeah, maybe they'll let UDP traffic come in, but they're not going to let people try and proactively send things in. They will let people send TCP packets proactively in to look at your website or to ask your DNS server a question or to send you email, but they will not let UDP packets in. That's a common decision by network managers. And you get a lot of control over that. On the other hand, with TCP connections, you want these things to be fair. And it's not that one computer should be able to send as many packets as the other. This is on a per connection basis. So if you look at a browser, for example, browsers don't just have one connection going on. So I'm going to open up Wireshark, and I'm going to look specifically for a particular type of connection while I go to the New York Times. God, this machine is slow. It's just unbelievable. TCP, what do I want to look for? Connection SYN. So that's the first packet in a handshake for TCP. SYN, SYNAC, ACK. Those are the 3 ways, and then you have your connection out. All right, so I'm going to filter for that on my Wi-Fi connection. And now I'm going to go to the New York Times. So I'll shrink this down so we can watch what's going on and hit return. All these are TCP connections. I don't even see anything yet. So these all were sent simultaneously at the same time. And they are gray because the other side maybe hasn't agreed yet to allow those connections to come in. But there's just like boatloads of these things. The green ones were allowed. So I sent out lots of tries, and a lot of these things look like they were ignored. But they have sequence numbers that are going up, port numbers that are going up rather. So that's I mean, we could just sit here and watch this go on, but my point is, even one browser can compete with itself for the bandwidth by opening lots of different TCP connections at the same time. So it's not that the machine gets 1/9, it's that you add up all the TCP connections that are trying to send stuff into a router that is trying to cram all of this stuff across a smaller link. Everybody shows up with their traffic from all these TCP connections, and they're all trying to get on the next ferry boat to go across the water. And basically what this is saying is you will take the same number of scouts from each scout troop onto the boat on average at the same, at the time. Nobody's going to get to load it up first. It's fair. It's completely fair. And this is supposedly the way it works at merge points on freeways as well. In fact, we get a little pissed if somebody tries to like go two people. No, it's one, then you, then me, then you, then me, then you, then me, right? And when people try to cut around it, and they're considered to be misbehaving when they do that. So you should come to Monterey for a while sometime, and you will completely readjust what you think is bad behavior here. You will come back here and go, is that all? Go ahead. So the rule in every city is different. It's interesting. All cities have kind of different cultures for driving. The one in Monterey, I would say, is if there's pavement, use it. And then let them. I mean, it's, there's not like lots of honking all the time. There's more honking in Monterey than in Mexico City because they're closer to the United States and we're a bad influence on them. We love using our horn. We drive with our horns. But, these guys go over the bumps and all the little things. They drive by braille. It's like, whatever. Okay, I must be at the side of the road because I'm hitting those little bump things now. So it's kind of interesting. But the idea is somehow or another it's supposed to be fair. The routers can't do much to slow things down. The routers do not run TCP. The routers stop at the network layer. So because of that, they don't run TCP. They don't know if packets need to be retransmitted. They know that they've dropped something, and they'll send you an error message to tell you about it. But they do know that they're getting busy. And so what they can do is a packet passes through them with this special explicit congestion notification pair of bits. They can set them both to 1s. And they're basically saying, I really don't know where this traffic is coming from. I mean, like I can see the IP address, but I don't really have any idea, is it coming from the LAN that I'm connected to, or is it coming from the other side of one router, or the other side of 10 routers, or the other side of 50 routers, or combinations of all of those things, which of course is true. Traffic's arriving at a router from all kinds of places. And so I don't know who's doing it, but I'm going to start setting these bits to let people know that are sending things through me that I'm getting congested. Those things do not go back to the sender immediately. There's bits that are set in a packet as it's being routed. So it continues on its journey. You just put a sticker on the side of the car as it passes through. When it gets to the far end and gets up to the transport and application layer, the transport layer at the other end goes, oh, wow, this thing showed up with a couple of dings in the fender. Somebody set these ECM bits. I will send via transport, because I do have a connection open to the other host. I will send a packet back his way. I'm going to send one anyway to acknowledge this. When I do, I'm going to let him know that one of the routers along the way complained that you're wearing me out. So you might want to slow down a little bit. So you can choose to do something about that. So there are schemes that have been developed to let routers try and complain. Of course, that takes a long time for that to get back. Right? So what you want to do is set those bits in enough time to where they can continue their journey, reach the destination, give the host at the end a chance to set those bits in an acknowledgement, which may take a while for them to decide it's time for an acknowledgement, and then work their way all the way back to the front to let this guy know to slow down. And then when he decides to slow down, it's going to take a while for that slower rate to kind of work their way back to the router. So the router is going to continue to get beat up for a while. So you want to complain early on. Right? So you kind of have a way of feedbacking this yourself. If you've ever worked on a project where you're supposed to be pasting things on, like an art project or an assembly line or something, you're keeping an eye on your supply, and you kind of figure out how long it takes somebody to go get you more, and you ask for more so that they have time to go there and get it before you completely run out. This is no different than deciding when to go to the store and how much milk to buy. You do this constantly in every aspect of life. But TCP and routers have a way of doing this as well. So we started off talking about the application layer in Chapter 2. Chapter 1 was kind of an intro to everything. And the application layer was HTTP and SMTP for email, and we looked at some other application layer protocols as well to do things like point-to-point and client-server and stuff like that. What we've looked at in Chapter 3 is the transport layer, UDP and TCP. So the next chapter is talking about routers, and I'll take a break for a minute and show you a, have I told you the Nexus chips story, the Nexus switch story in Mexico? I can't, okay, well, this, okay, all right. So this is when I used up all 9 lives of my luck in one visit. So 2 years ago, maybe, coming up on 3, I found out that we were going to start having a user conference. First year, I heard about it anyway, at Cisco. And the conferences are called Cisco Live, and the big one's in Las Vegas, and it's got 25,000 customers that show up. You know, it's a big company, and they've got lots of customers. They build the infrastructure that runs the world's internet, after all. And they have one in Berlin that I went to once and will never go again because it was too freaking cold. So they do this when it's cheap. So in Las Vegas, it means in the middle of summer, and in Berlin, it means in the middle of winter. They have one in Australia. It's very nice. People have gotten to go there. But they also decided to have one in Cancun because the Latin Americans doesn't all make sense for them to try to come to Las Vegas. We're not all that friendly. It's hard to get visas for some of these guys, especially now. And you know, it's a different sort of tight culture around all of Central and South America. They all sort of identify as a group. So they got permission to pull it off, and they had been killing it. So the chairman said, sure. So they held this thing in Cancun. And you better believe my hand went up like this. I'll go. And I'm in Houston, and I had the Latin American territory anyway, and so I basically browbeat my way into this position from our group, and said basically, you know, you're all going to have to fly over me if you're going to try to get to Cancun, and I'm going to shoot you down if you do it. So just don't even go there. This is my territory. Stay the hell out. And so they said, okay, okay. So I kind of lied a little bit. I didn't really speak very good Spanish at all at the time. And that's become more evident to me as I continue to learn more. And I look at that point and go, that really was like I keep moving down how. But I agreed to go to translate for this Indian product manager who had this software solution. And I had the space right next to, we were at the end of one of these rows of booths, and right next to us was a Nexus switch, which is one of the big expensive switches that we make for data centers and for large companies. And there was like a demo unit sitting there. And so I, by Tuesday or Wednesday of the week, I'd gotten brave enough. I started to be curious, and when I was bored and stuff, and it's not often I actually get my hands on this stuff. And so I pulled those things out, and it's a Nexus 7702, and pulling the cards out and started inspecting it, and things like that. Nobody was really paying attention. There's no power cords here or anything like that. It's not working model, right? I mean, it's just kind of sitting here as a demo. And as it goes on, I get braver. I actually do one of my computer architecture, maybe it was a networking class, via WebEx. I had to give one from Cancun. And so at one point, I take my phone and switch it'll run WebEx as well, and make it the host. And I go down and I film this thing, and I show people, what's going on with it and stuff, and take a bunch of pictures. And a bunch of them were crappy and stuff, but you can see all the silver parts. Those are all the radiators to disperse the heat from all these chips. So this thing's kind of a fire-breathing dragon. And this thing generates a lot of heat, and these are all radiators up here as well. All of these are, they're just all over the place on this thing. So, I'm talking to students or something, and somebody's like, well, where are the chips on this thing? I go, well, they're underneath the radiators. And I go, well, why can't we see them? And I'm like, yeah, why can't we see them? So I decide I'm going to disassemble this Nexus switch. And so I'm taking them some pictures and showing things like everything else on Earth that's built by Foxconn. So Cisco doesn't own any of its own assembly lines, and nobody really does anymore. And I decide, here's some high-speed content addressable memory that's in there, I think. And so these radiators, these little fan blade things, are glued to chips with special heat transferring paste. That's not an insulator. It will pass heat very, very efficiently. So it's not like styrofoam. It's more like, I don't know, air or something, or maybe water. So you glue this thing on there, and the glue can't be an insulator because you need the heat to pass through this paste and then into the blades of the radiator and dissipate. That's kind of the whole point, to suck the heat out of this thing. So, they're on here with these clips, and so they're just undo the clips, and you can pull the thing off, and then you kind of have to work at it a little bit because it's like stuck on there, but you can pry the thing off, and you can see the residue from the paste here. And you can take these things off. You're supposed to have this toothpaste tube of this paste, though, and put it back on and, kind of glue it back on. Well, I didn't do any of that, but I was just showing, like, this is a custom ASIC. This is the secret sauce. This is where the magic stuff happens, and this one is not built in China because of intellectual property concerns. This one's built in Canada or someplace elsewhere. And here's a little spring-loaded clips that you can use to take the thing off. And so when I'm done, showing all this, you can see it's kind of hooked under here on this hook, and it kind of works its way here. So you just pop it out from under this, and the thing will come off. I just put them back on. I didn't put them on with paste or anything, and nobody's paying any attention to me whatsoever. I'm having a great old time. This is a crystal, by the way, and I don't know, maybe 10 days after the show, maybe something like that, this email goes out to everybody who worked at the show. Who the hell took my Nexus 7702 switch apart? And I'm like, oh, it's like, this is my lab equipment, and the thing overheated, and it's like fried now, and it's $250,000. And I'm like, yeah, well, who leaves $250,000 worth of stuff sitting alone by itself in front of 6,000 people, 6,000 Mexicans? I mean, I was trying to I laid low, let me tell you. And my product manager instantly wrote me a note, and he goes, don't worry, your secret's safe with me. And I was like, oh, thank God. So I managed to build up a little camaraderie, but I was practicing my defense. Like, okay, if it had been gold, would you have just let it sit there? No sign that says no tampering, no plastic box over it, nobody to watch it. Don't even tell the people that are next to it. You just set it there and go, okay, you may begin, and then leave? I mean, what kind of an idiot does that? So, I'm trying to teach people about this stuff. If you don't want me to teach with stuff, then don't put the tool in front of me. Fortunately, I never had to use that excuse, but it scared me pretty good, I will tell you. This is one of those CLMs. I told you, it's an acronym you'll hear in your career. Ooh, Bob pulled a CLN today. Did you hear what he did? He ran his motorcycle. He ran his car into the boss's motorcycle in the parking lot. Ooh. So, all right. So we're back to the topic at hand. What I want to do is spend some time now going through one of the animations in excruciating detail. You need to know exactly what's going on in a graph like this. So let me find one that I like, so I can copy it over. And usually after 4 or 5, okay, this one's interesting enough. We'll grab this one. Okay, everybody eat their Wheaties this morning? You're going to need them, because this is going to go deep. Let me pop up another slide and paste this guy in. That may be a little too much. And we're going to move it up to the top. Okay, now I'm also going to put a table in here. And I don't exactly know how many columns I need. I can't ever quite remember. But I think it's officially a bunch. So we're going to put a bunch of columns in here. What they need is a table tool. All right, that ought to be enough. And what we're going to do is go through what's happening in this graph. So first of all, does anybody know what this is a graph of? Yeah, so it's the size of my window, which basically means the number of packets that I'm going to send out at the beginning of the next round. Am I going to send one? So if you remember the other animation tool I used, where we had some of these other things to kind of play with, I think it may have been this one actually. Yep. We had selective repeat. My window size is 5. I can send 5 things out at a time in this round. And the window size never changes in this animation. It always stays as 5. It slides. It will move over when I get acknowledgments and things, but the window size stays 5. But that's not really how TCP works. TCP starts at 1. And when it's at 1, you are in what is called slow start mode. So we need to define a couple of variables first. First thing is, how many bytes are in one of these packets? Because remember, I've told you TCP really only tracks bytes. So at the layer 4, we are dealing with segments. Remember, it's bits at the physical layer, frames at the data link layer, datagrams at the IP layer, segments at the transport layer, and messages at the application layer. We do this just to continue. Or as everyone on Earth calls them, packets. All right, all of them, top to bottom. So I have a maximum segment size, and let's say it's 100 bytes. All right? And let's say the total number of bytes that I need to send is 10,000. So how many packets am I going to need to send? $100. Yep. It works better if you guys participate. It tells me that you're actually paying attention. So the total number of packets I'm going to need to send is going to be 100. So I have my round number. I'm going to start off in round 1, and I'm in slow start mode. So in slow start mode, I want to send 1 packet. Later, I'll be in congestion avoidance mode. So I want to know how big my window size is. And my window size right now starts off at 1, so it's going to hold 100 bytes. So that's why I say I'm going to be sending one packet. What I'm really tracking is that my window size is 1 MSS's worth of bytes, right? Because I'm really counting bytes. So let's pick a starting sequence number to get things started off with. And let's make this easy and make the sequence number 0. All right? So I have my starting sequence number here, and then I'm going to have an acknowledgement that comes back in a minute. So my starting sequence number is 0, and I send in round 1 MSS's worth of bytes. The MSS is how many bytes I can fit into a single packet. Therefore, since my window size equals exactly MSS, I will be sending 1 packet's full of bytes. So I send it over. I'm in slow start mode. I will acknowledge by adding 1 to the last byte number to let the sender know I'm ready for this byte next. So what will that number be? What's my acknowledgement number going to be? What's the next byte number that I'm ready to see the sender transmit in my direction? Nope, I sent 100 bytes. Remember? 100 bytes. So what's the next one going to be? What was my first byte number? My first byte number is the sequence number, right here. It'll be 100. It won't be 99. So this throws a lot of people off. If I start with 1, it's really confusing. So if I start with 1, then it's 1, 2, let's say it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Your next byte number is 11. But because we like to start counting with 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, your next byte number is 10, not 11. So this makes it nice, even numbers, but I just want to make sure you remember that it's kind of tricky a little bit, and people can get a little bit lost by that sometimes. Okay, so I'm now ready for round 2. And the way slow start works is that for an acknowledgement that comes back, the acknowledgement will have implied in it the number of bytes that have been successfully received. And there have been 100 bytes successfully received. That is why he acknowledged that he's ready for the 101st byte, number 100. See how it's a little confusing? So the way slow start works is it says once you get an acknowledgement back, you add the total number of bytes that they are acknowledging having received to your congestion window. So my congestion window is going to go from what it was before plus, in this case, an MSS for every ACK that comes back. So this ACK will acknowledge 100 bytes. That's an MSS's worth of bytes. That makes sense because that's what I sent it. In one packet was an MSS's worth of bytes. So when he acknowledges it back, it would be very odd if he didn't acknowledge the whole thing. So I'm going to add that. Therefore, that's 2 MSS's worth. So I'm going to send 2 packets in round 2. I get 2 acknowledgments back. Each one of the acknowledgments, it goes from 100 to 199 and 200 to 299. The next byte I'm ready to receive is 300. So I've received acknowledgments for 200 back. Each one of those is going to add to my congestion window. So now my congestion window goes from 200 to 300 with the first acknowledgement and from 300 to 400 with the second acknowledgement. So for round 3, I can send 4 packets as a result, starting at byte 300, and I will acknowledge what byte number. So I sent 3 to 399, 4 to 499, 5 to 599, 6 to 699. So the next one after that will be 700. Tiny bit tricky. That's why we're going through this. So I've sent 4 in the next one. Now it's time for round 4, and I need to introduce something that's very difficult to see on this diagram, but if you look closely, you may see a little red hyphen right here. So that is my setting for, I need to make this not very big. That's my setting for a variable called slow start threshold. All right, so that's the current value that the operating system has set as a hint that based on past experience, it believes is as far as I should stay in slow start, as far as I should continue to grow exponentially before I start growing linearly. And when I grow linearly, that's when I enter this sawtooth mode. So that's kind of what it's saying. You've now entered, the sawtooth mode. So I'm not quite there yet because slow start threshold is set to 8 in this case. It's often set to a power of 2 at the beginning. So this is the operating system's advice. It's part of your TCP stack. So for my next round, I am going to take each one. I'm still in slow start mode for now, so I'm going to take each one of these 4 batches of 4 sets of ACKs that I've got, each one which acknowledges having received 100 bytes, and I'm going to add them to my congestion window. So it's going to go 400, the first one, 100, let me just draw it out in detail. I have 400 to start with. I'm going to add the acknowledgments for bytes 300 to 399, and that's going to set my congestion window to 500. Then I receive the second acknowledgement for bytes 400 through 499, and that's 100, so I'm going to add that to here. I start at 600, I receive the acknowledgments up to 599, it sets it to 700, and I'm at 700, and I receive the acknowledgments up to 699, which is the last one because he says I'm ready for 700. That gets me to 800. All right, so now my congestion window is size 800, and I'm at slow start window size of 8, but now I transition over to congestion avoidance. So I'm going to switch my rule. I am no longer going to add this way anymore. So I send 800 bytes out. My segment size is 100, therefore it's 8 packets that I'm going to send. That's what's happening right here. My 8 packets go out the window starting at 700, and my acknowledgement that comes back is going to be what? Start at 800, I send 700, 1500. This part, you can just add these things together. Right, you see that? I'm just adding these things together. All right, salutes. So now I'm ready for round 5. Round 5, the math is different. And if you look at the equation, this loses tons of people. Conceptually, it's very easy. When you look at the details, it's super obtuse. So now what your congestion window is going to be congestion window plus congestion window times your acknowledgement divided by congestion window. And you're like, what? I think I have that right. So what this basically is going to do, let me draw it out for you. Let me do it as the math simpler. The math might be a little bit easier for us to wrap our heads around. If my congestion window is currently set to 800, I'm going to add to it whatever acknowledgement you got, which is an MSS's worth, divided by 800, and I'll eventually grow this by 800 up here, but I'm going to just start with the first acknowledgement. So what is that going to get me to? That's going to get me to a window size of 812.5. And then another acknowledgement comes in, the second one, and it's going to get me to 825. The third one gets me to 837.50. Wow, I'm struggling to keep up with my pen. The fourth one gets me to 850. The fifth one, 862.50. The sixth one, 875. The seventh one, 887.50. And the eighth acknowledgement that comes back gets me to 900. So when I'm in congestion avoidance mode, getting all the acknowledgments back for a round of transmissions grows my number of packets by 1, from 8 to 9. Once it's at 9, this equation changes. I started off with 900, and I'm going to be dividing by 9. So clearly, it's going to take 9 of these things to grow this to make it equal a full 1. Right? Anything less than that, and it's a fraction of 1. 100 900th is 1/9. 200 900ths is 2/9. Not until I get to 900 900ths is it equal to 1, 1 MSS, then therefore I can grow from 9 to 10. So when I'm at 9, I start off at byte 1500. I'm still sending, no, that's not right. My window size is 900. I start off at byte 1500, that goes in this column, and I'm going to acknowledge back what? 2400. I still add these things together. I started at 1500. I sent 900 bytes. I'm ready for 2400. So I'm still making lots of progress. Even though I grew this by 1 packet, it's still a lot of packets in the window already. So I still send 900. I get to round 6. I know that I'm going to have 1,000 bytes. Therefore, I can send 10 packets. I will start at 2400. And I will end with an acknowledgement coming back saying I'm ready for 3400. All right, so that gets me to 8, 9, 10. At packet 11, round 7, something bad happens. And I'm going to have grown my window to 1100 bytes, so I can send 11. And I drew every one of these in the wrong column because these are supposed to be over in the congestion avoidance column. I can't learn. I did the same thing yesterday, too. Caught myself doing that. So I'm going to start with 3400. Now, here's where this table is going to fall apart. But we're going to keep with it because it's impossible to know exactly what happened. These graphs don't really show you everything going on. So what I think is going to happen is I'm going to acknowledge back 4500. Correct? That would be what I would acknowledge back if I correctly received all 1100 bytes they dumped at me in this window that arrived in 11 separate packets. They couldn't fit all of them in one, so they had to send me 11. But there was a loss when this happened. Some packets didn't make it. There's 2 ways you can decide with TCP that a packet hasn't arrived. One way is for the timer to go off. That's very, very bad. That means that you waited an extraordinarily long time, plenty of time, usually twice the amount of time, something like that, for that packet to have made it and come back, and still no word. This is like losing communications with your spaceship. You wait, you wait, you wait, you wait. Like for some of these things, you'll wait months. Like the Mars lander, you'll just wait months and months, and then you'll finally declare it dead. You know, you'll wait months for things like maybe the dust will blow off a solar panel and it'll gradually recharge the batteries enough that it can start itself back up again and answer. We're waiting on things like that. So TCP is patient, but when a timer goes off, it's a sign that something bad has happened with the network. Why? Why is something so awful? Because there's a second way to know that you've lost a packet, and that one lets you react much more quickly, and it's the triple duplicate ACK. It's like a triple reverse somersault on the gymnastics mat. It's really kind of cool. It has a hell of a dismount, I got to tell you. So triple duplicate ACK is what happens when you are sending packets and you keep getting the same acknowledgement back. So if I'm sending you packet 500, 600, 700, 800, 900, and 1,000, and 500 gets dropped, what you're going to acknowledge back is you're not going to acknowledge anything back for 500 because it never arrived. When 600 arrives, when the packet that starts off with sequence number 600 arrives, you would expect the person at the other end to acknowledge, I'm ready for 700. But they will not. They will acknowledge back, I'm still waiting for the packet that starts with 500. So you got an acknowledgement for a packet that had already been acknowledged before. Because before you ever sent 5, 6, 7, 8, 9, and 10, you would have had to have been given permission to start sending 5, 6, 7, 8, 9, and 10. Which means you would have received an acknowledgement telling you that it is ready to receive bytes starting with 5, 6, 7, 8, 9, and 10. So you got an acknowledgement already for 400 through 499, and you received an acknowledgement saying, I'm ready for 500. That's an acknowledgement, number one. You send 500, it doesn't arrive. You send the packet starting with 600. What you're hoping for is that you get an acknowledgement back saying, I'm ready for 700. You also were hoping to get one back saying I was ready for 600. But your window gave you permission to send 5, 6, 7, 8, 9, 10 all at once without intermediate acknowledgements. So you sent 5, 6, 7, 8, 9, and 10. Your window size was that big. So what you got back was not 700. You get back 500 again, saying the last thing I got in order was 400 through 499. So I'm sending you another acknowledgement to let you know that I did get something from you. Thank you very much. I did get a packet from you. But my acknowledgement number that I'm going to give you back is a hint that I still haven't received the packet starting with 500. So I'm going to send you that number 500 again. That's a duplicate acknowledgement. You send it packets 700 through 799. They've all been sent at once. They're all just arriving one right after the other. 7 through 799 arrives. You would normally get back an acknowledgement for 800, but you are still at a situation where the receiver is still waiting to get the packet that starts with 500. So he's going to send you that acknowledgement again. It tells you the network is working. There are packets that are making it across. It's not down. It's working pretty well. Now 2 more packets have made it. In fact, they didn't take very long to get there and for me to get the acknowledgement back. But it's just that the acknowledgement's not the one I expected. So I don't know which packet you're receiving, but I know it's not 500. I'm figuring that out. So this is the second duplicate for the original ACK. I send 8 through 899. I get acknowledgement back 500 again. Now it's the 4th acknowledgement for 500 I've received, the triple duplicate acknowledgement. And that's the point where you say, okay, that's enough. I've sent 4 packets out. 3 of them made it. The last 3, the first one never did. It should have arrived, and I should have gotten an acknowledgement by now. Don't know what happened. They obviously did not get it. I know that it wasn't a simple case that the acknowledgement didn't make it back to me, because they would be sending me higher acknowledgement numbers. If the acknowledgement had gotten lost, they would be acknowledged. But the packet obviously never made it, because they keep sending it on. So I'm going to go ahead and stop right now before the timer goes off, and I'm going to resend packet 500. It's clear to me now what's going on. You never got packet 500. So the behavior that you exhibit on this graph is different with those 2 scenarios. Again, the first one is the timer went off. The second one is a triple duplicate acknowledgement. So here's what happens. When you don't go all the way down to 1, it's a sign that it was a triple duplicate act. Triple duplicate acts are, timeouts are obvious because your window size drops all the way back down to 1. Okay, but that's not what happened here. When your window size shrinks, it's one of those two. It's either timeout or triple duplicate act. And the fact that it didn't go down to 1 tells me at this point that it was a triple duplicate act. So here's what you do whenever there's a loss. Always. The first thing you do makes no difference which type it was. The first thing you do is you set your congestion, let me be really careful with this. You set your new SS threshold, the new one going forward, equal to the last congestion window that you had, the one where the error occurred, divided by 2. So what was my congestion window? Well, it was 8, 9, 10, 11. That's what we see down here, right? We agreed that it was 11. So the first thing I need to do is move my threshold to 11 divided by 2. You can be conservative and make that 5 if you want. That would be okay instead of 6 because it's 5.5. So you got to figure out if you're going to go up or down. So let's just make it 5. And I'm going to set it right here. So this is my new SS threshold. So that's where you're going to start your next round of transmission. You're going to start your next round, and you will be at 5, typically, if it's a triple duplicate act. So the second thing I got to figure out is it really going to be 5 or is it going to be something else? Here's where the second stage comes in and where the difference exists between the two types of errors. Now that you know what your new threshold is, if it's a triple duplicate act, then you're going to set your window size equal to the threshold size. In other words, you're not going to drop it all the way down to 1. You'll just drop it back down to the new window. If it was a timeout, simple. Your new window size equals 1. All right. Got it so far? So if that's true, this was a triple duplicate act, so my congestion window should have been set to the threshold. But my threshold's equal to 5, and we can all see that my congestion window is not. My congestion window is 8. Why is it not 5? Well, this is an enhancement that was made to TCP Reno along the way, and it's part of this simulator. And it's actually what we do, so I'll describe it to you, but it's a little confusing. So here's the idea. I had my window size at 11, and there was a loss. So I would have dropped it on normal occasions. I would have dropped it had I known right then, for sure, I would have dropped it to 5. That's what our math just showed us. I was at 11, I had a loss, I dropped it to 5. But is that the only thing that happened? No. I continued to send more packets. That was not the last packet I transmitted. Yes, 5 was lost, but I sent 6, 7, and 8 as well. I know that because that's what gave me the triple duplicate acknowledgments. So what would normally have happened if I'm back at 5 and I'm in congestion avoidance mode, growing 1 by 1 by 1, and I was at 5 and I had successfully sent another packet? What would my window size have done after getting that acknowledgement back? It would have grown to 6, right? And then what would have happened when I had a window size of 6 packets and I sent all 6 and I got acknowledgments back for all of those, and I would have grown to 7. And if I'd have sent 7 packets and got them back, I would have grown to 8. Because I did send 3 more packets, why don't you just give me credit for those and go ahead and grow my window 3 more? So in every case, 100% of the time, what you will find is that this will be SS threshold plus 3. For those 3 packets that were part of the triple duplicate act. So that's why the window size goes back to 8. All right. Immediately after 8, I have more bad luck. This time the timer goes off. Turns out it wasn't just a hiccup. The network was about to fail. I got lucky. I only dropped 1 packet when it was 11, but now nothing's coming back. At least I don't have enough to trigger a triple duplicate act. Maybe I got back 1 or 2. It also could be that the one that was lost was the very last one in my window, and I don't know. But, you know, I decided timer went off. I decided was bad, so I grow all the way back to 1 at this point. So for round 8 and round 9, I'm back to 1. This means my congestion window is 1. This means my congestion window is 8. I can send 1 packet. I can send 8 packets. If it goes back to 1, you're all the way back and slow start again. And you're going to grow 1 to 2 to 4 to 8. And at that point, you crossed the threshold. So you will not grow exponentially. By the way, I think this is wrong. I think you would stop at 5, but that's okay. We'll continue on. 1, 2, 4, 8. You cross the line in the middle of growing your window size. So let's say it's 8. I'm now going to grow linearly 9 and 10. I'm at 10. I have a triple duplicate ACK. It normally would be 5, but I add 3 to it, so I'm at 8. 9, 10, 11, 12. I have a loss. It would normally be at 6, but I'm going to add 3 to it, so I'm at 9. 9, 10, 11, 12. I get all the way up to 21, 22, 23, and the timer goes off. I go all the way back down to 1, but I have to set my new threshold. It was at 23. Half of 23, round down, is 11, correct? So my new threshold is going to be 11, so I will grow 1, 2, 4, 8. I will cross that threshold in between 8 and 16, so I will grow to 16. I think you grow to 11, but I do need to look at the code again. At 16, and then I have another timeout loss, and I go back down to 1. So that's what's happening in excruciating detail on these diagrams. So if you don't get it, either listen to this part of the recording again, or go to yesterday evening's lecture. I did the same thing, but it was a different example, and you need to master this. You will have this diagram on the final. You will have it in a homework. I will also give you a table that says, fill this table in. You start off in slow start, your threshold is this, your MSS is this, here's the total number of bytes you've got to send, and here are the events that happen. You have a loss at round 5, 11, and 15. Fill it out. So you got to know whether you're in congestion avoidance or slow start, you got to know when to switch, you got to know how to grow the window size, you got to know what to do when there's a loss. I have to tell you whether it's triple duplicate or a timer, etc. You have a question? This diagram isn't exactly in the book. It's in this simulator. So, and it will, if you look at the solutions, it will go into great detail down here at what's going on. All right, it's a huge help. You click on another problem, it will generate another one, and another one, and another one. Every time it's different, and every time if you show the solution, it will show you at the bottom what's going on. It's, we used to have to teach without anything like this. Can you imagine? I mean, this is unbelievably helpful at figuring out what's going on. Yes, the simulator does the same thing every time. This one doesn't have any of those losses, which is actually quite amazing. So we need to find one that does. This one does. I was at 10. It went down to 5, but you can see it's really at 8. So if you scroll down and look at the solution, it was at 10. It went down to 5. You can see the threshold at 5, but you set your window size to 8. All right. All right, guys, I'll see you on Thursday morning on WebEx. Uh-oh. I hope people muted eventually. All right, have a great one, guys. I hope there was not noise like the whole time. That was my fault. My bad. And watch, there'll be like locusts piling